Welcome back, guys. This is the one that's titled Work Energy Review that has top 5 on the top of it for work energy with calculus. Start with this comic. Read this. It'll change you. 1 over x, we have x squared. Reads it and becomes 2x. Then we have 2x. Passes the book on to E, tells him it'll change him. E changes it, and it didn't change it. And it said, how can anyone not be affected by this book? It's a derivative. That's a physics joke, or a calculus joke. All right, so where are we going to see this energy? When we see things like roller coasters, hills, things that are swinging, when we have springs. And for us, this is going to be always conserved as long as we have no non-conservative forces. So what would non-conservative forces be? Non-conservative forces are typically, for us, friction and air resistance. And I'm going to cover air resistance in the next section with you guys. We'll go get into how to calculate the drag force on stuff, because it does relate to E and the natural log. So our energies are the spring energy, which is 1/2 kx squared. Potential energy of position, which is mgy. Kinetic energy, that's 1/2 mv squared. We also have the work energy theorem. So if there are non-conservative forces, we can find out how much work is taken out of our system. We have our power, which is our work divided by time, and it can also be equal to an average force times a constant velocity or an average velocity. And again, this is the dot product. So this is combining 2 vectors, parallel components, to get a scalar. And so our answers are going to be always in joules for energy and in watts for power. And I'm going to do a couple examples with and without calculus for you guys, just to review a little bit, as well as you guys have the multiple choice that have with and without calculus on them. All right, so a 1 kilogram block slides down a frictionless, 20-meter high incline. Find the max velocity. How far could the block compress an ideal spring with a spring constant of 100? So when it's at the top, it's going to have all potential energy of position. When it's at the bottom, it's going to have all kinetic energy. As usual, I can make the masses go away, and I can see that my velocity is going to be 2 times -10 times -20, which is going to be plus or minus 20 meters per second. Our block's going to slide down, and now it's going to compress a spring. So now, again, I can say that my mechanical energy was conserved. And in this case, I can say that mgh or mgy is equal to 1/2 kx squared. And so we're assuming this is an ideal spring. You guys will have non-ideal springs because you'll be able to calculate things with calculus that they couldn't without calculus. So I can find out what x is by multiplying by 2, dividing by k, and square rooting. So this is going to be 2 times 1 kilogram. Again, we have -10 and -20. And then we're dividing this by 100. So on the top, I'm going to have 400. On the bottom, I have 100. So 400 divided by 100 would be 4, and the square root of that would be plus or minus 2. So 2 meters. And again, unless they tell us that we have friction or air resistance, we're going to assume that we don't. And they would do that just by saying something's rough would be enough for them to say it. All right, so added stuff that we need to worry about, escape velocity. Our energy or work being the integral of f dot dx or f dot dr. That power is the derivative of energy with respect to time. And then the relationship between our force and our potential energy. And these kind of go together. And I had a whole set of notes that I went over on the videos, which is just potential energy curves. So hopefully you've seen that and the other Ed puzzle where we pick out the equilibrium positions, we pick out what the force is, knowing the energy, find the kinetic energy, knowing the energy. That's a topic that does not show up on AP Physics 1. So first off, escape velocity. So escape velocity is going to be just enough energy for us to get free of the gravitational pull of a planet, but be left with no energy besides that. So make this a little bit smaller. We're saying that we would have this special energy, which I would call VE. And we would have the potential energy between the planet and whatever object you're trying to get free of it. And then afterwards, we're far enough that we have no potential energy and no kinetic energy. And so you want to get VE by itself. The first thing you would do would be to add this potential energy to the other side. Remember, potential energy is negative. The way we define it, it's zero at an infinite distance away. And so anything that's closer needs to be less than that. And in these systems, the potential energy dwarfs the kinetic energy. So overall, the total energy of those two combined is always negative. So I'm going to add this to the other side, and I get that 1/2 mve squared equals gmm over r. I'm going to cancel out an m. Multiply by 2 in square root. So that's going to tell me that my escape velocity is equal to the square root of 2g big M over r. And so this is a universal constant. This is the mass of the planet we're trying to liberate from. And this is how far we started from the center of mass of that planet. So very often, if it's the surface of the planet, it would be the radius. And that's an advantage from taking off from a higher altitude, or for us to launch from the moon and not from the Earth at all, because our escape velocity would have to be a lot less. So, and that is essentially how much energy we have to get, right, to get free of it. All right, so this is on our equation sheet. So is big G. It's 6.67 times 10 to the negative 11th Newton meter squared, kilogram squared. Little m is the mass of what you're trying to liberate. Big M is the mass of the planet. Sometimes it's an asteroid because you don't have to get very far from an asteroid for it to make a pretty big difference, or a moon. And like I said, r is the distance from the satellite to the center of mass of the planet. And so we want to have just enough kinetic energy, like I did in driving it, so that we have no energy to be left with. All right, so what would be the needed escape velocity for a planet that had a radius half that of the Earth and a mass that was 3 times as much? for the same rocket. So we're saying that our escape velocity was radical gm times 2 divided by r. So for problems like this, when they're asking you how one thing changes another, I would encourage you to put in ones and see how that changes. So 2 is not going to change. So even though it's 2, I'm going to put in 1. My universal constant is also not going to change. But now my mass is going from 1 to 3, and my radius is going from 1 to 1/2. And so it looks like my escape velocity would change by a factor of radical 6. All right, in an experiment, a student wishes to use a spring to accelerate a cart along a horizontal level track. The spring is attached to the left end of the track as shown in the figure above and produces a nonlinear restoring force of magnitude F of S equals AS squared plus BS. Again, very often, and it seems weird, but S is used as a position thing. So that's our distance. S is the distance the spring is compressed in meters, and measuring tape marked in centimeters is attached to the side of the track. The student places 5 photo gates on the track at locations shown. Derive an expression for the potential energy as a function of the compression X. Express your answers in terms of A, B, S, and fundamental constants. All right, so our potential energy is going to be equal to the negative of our integral. And that's what the potential energy curve slides. We're trying to get. So this is going to be A S squared plus BS ds, which is just like a dx. And so our potential energy is going to be equal to AS cubed over 3 plus BS squared over 2 plus some constant C. So you could write it as this with the parentheses, or you could distribute that negative sign to each one of those terms. All right, a 3 kilogram object is moving along the x-axis in a region where its potential energy as a function of x is given as. I'm actually going to take a pause here, and I'll do this one on the next video.